So now we can look at the MO diagrams and how we would construct them for diatomic molecules. And so the first thing that we need to do, following the rules on the previous slide, right, is we have to identify the point group. Then we're going to get the atomic orbitals that we're going to use to make bonds, make molecular orbitals from atomic orbitals that have similar energy and same symmetry. We're going to figure out the symmetries of the MOs, and then we're going to populate the orbitals with electrons according to Hund's rules. So the point group. So this is a linear molecule, and both atoms are the same. So this is the D infinity H point group. We can pull up the D infinity H character table here, which we will have to consult. And what we are going to do then is list out all of the atomic orbitals. And here I've shown, some of the core electrons too. These won't necessarily really participate in any bonding, but you can draw them. You're not going to get necessarily a wrong answer. But really the focus is going to be on the 2s and the 2p, right? For oxygen, those are the atomic orbitals where there are valence electrons. The valence electrons are in the n equals 2 set of orbitals, and there's only 2s and 2p. And we know the 2p is going to be higher in energy than the 2s and going to be in 1s, and they're both oxygen, so the 2p sets of 2p's are going to be at the same level. The 2 sets of 2s's are going to be at the same level, and the 2 sets of the 1s are going to be at the same level. We don't know what those energies are. Strictly, we didn't consult any experimental data, but it doesn't really matter for the purposes of a lot of these MO diagrams. So then what we're going to do is we're going to look at the character table, and we're going to get the symmetry of the different atomic orbitals. So how do we do this? Well, we look at the character table, and anything that is an s orbital, that is always going to get the totally symmetric representation in this point group. Again, the totally symmetric representation in a point group is the ones that have ones across the board. So this is a little funky point group where you have Greek symbols for the Molekine symbols because it's linear. But it doesn't really matter. You're just looking for the first irreducible representation with ones across the board. S orbitals always have that ones across the board irreducible representation. So the s orbitals are going to have a symmetry of sigma g plus. So that's why here I've labeled all these 4 different s orbitals as having symmetry sigma g plus. Next, you have to think about the p orbitals. The p orbitals have symmetry. There's the px, there's the py, and the pz. And what's really nice about group theory and the character table is that those orbitals have the same symmetries as the x, y, and z vectors, respectively. So the px and the py, you can see they transform as the x and y vectors. Those 2 vectors transform together as pi u. And the pz orbital is going to have the same symmetry as the z vector, and it's going to transform as sigma u plus. So we have total dimensionality here. Or we're going to say our 3p orbitals transform as sigma u plus pi u. And that makes sense because we have total dimensionality of 1 plus 2 with 3p orbitals to start with. So our total symmetry should be 3. Total number of orbitals, our total dimensionality should be 3 of our representations. And 2 of those are degenerate in energy. They transform as a pi u, and the other pz transforms as a sigma u plus. So there we go. And so that's just written here, sigma u plus pi u, sigma u plus pi u. Now we put in electrons. Well, we know that oxygen has 2, 4, 6, 8. It's the 8th element on the periodic table. And so it's going to have 8 electrons. And again, we're populating this by Hund's rules. We're constructing a molecular orbital diagram, so it doesn't really matter if you get this right for the atomic orbitals, but strictly, right, we would unpair the electrons as much as possible. That's Hund's rule, maximizing spin when you have degenerate orbitals. And so this 4th electron in the 2p's is going to have to be paired. Now we can go ahead and make molecular orbitals from atomic orbitals that have the same symmetry and similar energy. Well, they're the same symmetry here. Both these 1s's are sigma G plus. They're similar energy. So we could combine these to give constructive interference. That would be a bonding orbital, and destructive interference. Just some nomenclature for atomic orbitals. We use characters that have capital letters. For molecular orbitals, we use characters that have lowercase letters. So that's a capital sigma in Greek, right? And then this is a lowercase sigma. We usually don't put any nomenclature to distinguish a bonding orbital, but if you have an anti-bonding orbital, you're going to put an asterisk. So this was the destructive interference. And now, why do I have a sigma U plus here and sigma G plus here? We have to think about how these orbitals transform in the symmetry space. And so, one thing so what I'm going to do is I'm going to go to the previous slide and just draw these, okay? And so we said that, a sphere is always totally symmetric. So what we can do here is first, let's just draw our oxygen molecule and think about, where the principal rotation axis is. That's going to be through the oxygen atom. So that's going to be the C infinity, right? That's the highest order N. There also, of course, is a C2 going right through there. This is perpendicular. That gives it the D point group, but that's not super important here. What's important is this C infinity, sorry. So that, remember, our principal rotation axis is always going to be defined as being our Z. So that's going to be our Z coordinate. Now we can define X and Y however we want, but we have to have Z going in that direction with how I've drawn this molecule. And then I could do something like, I could define X this way, and Y could be coming out towards us, right? It's obviously going to be perpendicular to X and Z. Doesn't really matter. You always have to have your Z's correct, okay? Otherwise, you're going to get the wrong answer. Because Z is defined in all the character tables by convention as being the principal rotation axis, it causes some problems, major problems, if you don't have Z defined in that way. So always make sure it's in line with your principal rotation axis. Anyway, so we can ask the question, what happens? How do you figure out the symmetry of those molecular orbitals? It's not just simply based upon the symmetry of the atomic orbitals from which it came. So just to be clear on that, you can see you had sigma G's here, sigma G pluses. In the bonding interaction, you ended up with a sigma G plus in the molecular orbital, but the anti-bonding was a sigma U plus. So why is that? You have to go through and figure out how these molecular orbitals, when you construct them, will transform, okay? So let's start with the bonding interaction. So that's when they're both the same shade, right? We have constructive overlap. So we're gonna apply all these symmetry operations to this. So we apply identity, and what are we gonna get back? We're gonna get back just the same thing. Then we're going to apply a C infinity, right? Well, what's a C infinity? That means just rotating it an infinitesimally small amount, and that's not going to do anything. So we're going to get back the same thing. So because in both these cases we got back the same thing, we're going to get ones on the character table. We can do a mirror plane. Now I'm not going to keep drawing them, but I'll just modify our pictures to draw them. So sigma infinity V, if we do one of the mirror planes here, oops, infinity V, that's going to be in the plane, right? That's not going to do anything. It's going to take white to white or light shaded to light shaded. That's not going to do anything. So we're going to get back the same picture. And all these, it turns out you're going to get back the same picture, okay? If you do an inversion, you take to the right, go to left, top to bottom, all of that, it's still just light shaded. I mean, essentially putting two spheres together makes just a bigger sphere. So I think it's pretty straightforward to see that, this molecular orbital is going to transform as sigma G plus. What about the antibonding configuration that we saw? I labeled it, it transformed as sigma U plus. That molecular orbital, right, looked like this, where we had one that was shaded and one that was unshaded. So if we do identity on that, obviously we're going to get a 1. If we do a C infinity on that, what's going to happen? Well, we're rotating those lobes like this. That's just going to get back those same sort of lobes, right? So that's doing a C infinity. What happens if we do a mirror plane? See in one of the vertical mirror planes. Again, that's just a mirror plane sort of cutting through here. So it'll change top and bottom, but but left and right won't flip. And so we have that stays the same here. We have 1s there. Now what about inversion? Inversion, something is going to happen that changes this, because now you've gone right becomes left, left becomes right, top becomes bottom, bottom becomes top. So if you do inversion, your lobe on the left now is going to be dark, and your lobe on the right is going to be light. So that's why we have a -1 here. It went to -1 of itself. Let's do an S infinity. What's an S infinity? That's a C infinity followed by a sigma H. Well, we know C infinity does nothing. We went through that thought experiment. But a sigma H, so we do a C infinity, it does nothing. And then a sigma H, that's a mirror plane perpendicular to the C infinity. So that's a mirror plane through here. And that is going to flip them. Right? So you're going to get a -1. And then we have an infinite number of C2s. Those are perpendicular C2s. And so that is a 180-degree rotation going through here. Right? That's a C2. And so hopefully you can see that that's going to bring the dark shaded lobe over into the light shaded lobe and vice versa. So that's also going to cause a flip. And so overall, we figured out that this molecular orbital, this antibonding molecular orbital, transforms as 1, 1, 1, -1, -1, -1. That's sigma U plus. So, that's something that people really get tripped up on, is that just because I started with a sigma G and a sigma G doesn't necessarily mean I'll end with a sigma G. I did for the bonding interaction, but not for the antibonding interaction. Okay. Same exact thing for the 2s orbitals. You're going to get a bonding interaction. That's going to be sigma G plus. This is the second sigma G plus that appears in the molecular orbital diagram. So I call this, the second highest sigma G that we have. This is the second sigma U plus that we have. It's an antibonding configuration, just like the 1 sigma U plus star. This is a 2 sigma U plus star. Okay. And then we have interactions with the P orbitals. So we can look at this. We have a sigma U plus and a sigma U plus. Those can make a bonding interaction. How did I get the sigma G plus? Again, I had to go through the same sort of logic and see how the various symmetry operations transform those that molecular orbital. And it turns out for this sort of shape, if you do an identity on that, right, you're going to get 1. If you do a C infinity on that, you're going to get back the same thing. You're going to get 1. Even if you do like a C2, let's imagine, right? Before we got -1 when we did one of these types of antibonding orbitals with the s orbitals. But here, right, this would go 180 degrees, dark to dark, and this would go 180 degrees, light to light. So it didn't remain changed. So anyway, you're going to get 1s across the board. And that's going to get you sigma G plus. And then you have the antibonding and the interaction up here. That's a third sigma U plus that occurs. It's an antibonding, so we give it a star. It's a third 1 in the diagram. 1, 2, 3, so we give it a 3. Again, using the lowercase letter for that's just by convention. And this one you can see is going to be sigma U plus, for example, if we do an inversion or a C2 on this, you know, let's just do inversion. That's going to take, because U means ingrata, right? So that's telling you that it's anti-symmetric with respect to inversion. Light is going to go to dark, and dark here is going to go to light. Dark here is going to go to light. Light is going to go to dark, doing the left-right swap. Okay. Lastly, we have the pi U's that we can combine. Again, similar energy, actually the same energy and same symmetry. So same symmetry, so we can combine them. We can combine them in a constructive way, and the symmetry ends up being pi U, lowercase pi, the first pi U molecular orbital, first molecular orbital of pi U symmetry, so we give it a 1. And then we have the anti-bonding one where this is destructive. These, by the way, I just kind of wrote as tilted, but they're really in the plane, right? So I just couldn't draw that too well. But these are degenerate sets. And again, you can look, you know, how do these transform? And you're going to have to go through the same sort of logic to show that this one is pi G and this one's pi U. So that's something we can practice in class. But then you're going to fill in all these electrons. We had 8 electrons on each oxygen atom, 16 total, 2, 4, 6, 8, 10, 12, 14, 15, 16. And there we go. That is our molecular orbital diagram. We know that there's a double bond in oxygen, so we can check that. We have 1 bonding, 1 anti-bonding, 2 electrons in each. So those are going to cancel each other out. 1 bonding, 1 anti-bonding, 2 electrons in each. Those are going to cancel each other out. And then we have 1 sigma bonds worth of electrons here, 2 pi bonds worth of electrons there. That's a total of 3 bonds. But then we have 1 pi bonds worth of anti-bonding electrons, right? 2 electrons make a bond. And so the 3 bonding electrons minus the 1 anti-bonding bond gives you overall 2. You could also use the 1/2 bonding minus anti-bonding rule that I showed you before. That also works. You have 2, 4, 6, 8, 10 bonding electrons. And you have 1, 2, 3, 4, 5, 6. So 10 minus 6 times 1/2, that equals 2, right? So as expected, we're getting a double bond in oxygen. One last thing to note on this, really this is not occurring here. We did write it, and why is that? Because these are core electrons, right? So it doesn't really matter if you show it like this. If these atoms could, if the electron wave functions could get close to one enough for there to be significant overlap, this would occur. But these are core electrons, so this, you know, strictly doesn't really occur to any appreciable extent because these are core electrons. They're shielded by the 2s and the 2p. But nonetheless, you can go through this exercise and show them as bonding and as anti-bonding. They cancel each other out and don't make any net bonding interaction.